Welcome to another edition of redoing physics, sort of. Yes, a contextual critique of how physics is presented in universities and such. And so I figure before we start this one, I will attempt, if I can find the right window to open here. Oh, I can do the transition. I forgot. Transition. There we go. I'll do some drawing first. A little bit of explaining context and all that. So as I've pointed out, they kind of say that these charges on insulators are moving through the insulator, and they're saying basically that charge is the atom being polarized. That is, it spends more, the electron spends a little bit more time at one end, and I don't think that's how the phenomenon of charge, anyway, the electrical component of the electromagnetism, which are the same force. It's only one force, that is the two kinds of forces, two poles, plus minus force, plus minus matter bit. Simple way to think of it: electron, proton, and there's two forces that are inversely sensitive, and they're changed in their proportion in the environment. So gravity's producing the two forces all mixed, and a magnet is filtering it, and charge is placing more of it, more of one electrons, versus proton heavy. So I would argue that the polarization of the atoms is more a function of the idea that the electrons essentially absorb, just like the Earth absorbs gravity or something. They're absorbing what the identity of an atom. So an atom has its identity based on how much of its force is shadowed. So you could argue that when the atom is in one condition, it will be proton heavy, and when in another condition, it will be electron heavy. And sort of a simple argument is you can shadow something more the closer you get to it. So when somebody stands in front of me, they're going to block all of me. If they're far enough away, they won't. Catch. Well, they will, from that perspective. This is where it gets a little complicated, right? So the idea would be, and like I said, I might say something backwards. Well, I didn't say I was going to do that, but that's the implication I'm setting you up for in terms of it works. It's just figuring out which way it works is always a little bit complicated. So if you had 5 electrons versus 6 electrons, the argument could be made that one atom, so there would be a difference. I would argue that it would get a little bigger because of that. But the argument would be that this atom that has 5, its net production of force, that is from a location, would be that it's mostly electron force. Yes, because of the distance. So the outside world will see it produce more brown reflections than red. So as stuff goes in, the brown stuff will reflect more often than the red reflects off red. It's kind of simple. And the other atom, the ion of the opposite ion, would be doing the opposite. That is, more red reflections would happen and fewer brown reflections from a distance. And that's sort of the definition of charge. And the neutral would be one that reflects an even amount of both forces. It's kind of simple. So I've done this analogy before, that I can adjust the size of these things to make them the same size, right? Yeah, keep adjusting the wrong one. This one goes bigger, this one goes smaller. There. Okay, now they're different sizes. You see, the big thing ends up being the same size as the little thing from a distance. And that's essentially the function. So as you make, so when those two things, this is the electron, this is the proton, are in balance, that is, they're the same size, okay, from the external world, that's your neutral. And as soon as one gets closer or further away, as soon as the electron moves in or moves out, it becomes dominant. So in this case, going out makes you bigger, and going in makes you smaller in proportion. And those would be your plus ions and your minus ions. So just to clarify that, then the other point I've been raising is this surface idea. So I'll just go over that one more time, maybe a little clearer. So you would have these ions on the surface of a substance. And the trick would be, as you bring two plates closer together, I guess I can draw the two, which is, I'm ending up drawing the same thing I drew the last time, but we'll see if it makes any difference, if I can say it any more clearly. So when they're close together, these attractive forces, or if they were repulsive forces, it doesn't really matter, but you'll get the idea. Let's say if it can attract or repel. The idea would be is that if they repelled, then you'd be pushing each other out further, and if you're attracting, you're going to be pushing each other in further. And the closer you are, the more stronger these forces get. So the tendency will be is for these other objects to move both this way and this way. So the thickness of the material they're filling gets thicker, so to speak. They create space. So they were one-dimensional, and then they become two-dimensional in terms of their space. So they double the amount of space they can occupy, in a sense, or triple or quadruple. And that ends up being the charge density capacity, the density capacity, you could say, of, say, an insulator. So its dielectric constant is sort of dependent on how able the ions are to move up and down on the surface. So glass has a number of something like 70, I guess, from what he said. The water. So it's kind of flexible, and you can kind of understand that because it has a weird surface tension to it. And glass is 5, and some other substance is 3, and then air is 1. So depending on how capable it is, air would probably be the limitation, is there's just not enough atoms. So, they don't, it's not a space problem, it's a density problem. There's not enough atoms to be able to, have a flexible surface. But that's what changes the amount of density you can have. And obviously, as you bring things closer together, their voltage, the pressure, would also increase. Well, in this case, the voltage increases as you separate them, because the voltage will be an expression of how crowded they are. So there's two components to the space argument. This is sort of like a way of analogizing it to voltage, which is pressure, versus amperage, which is volume, and then you have watts. So those are kind of the components of electricity, is voltage, amperage, and then the combination of those two equals how much total energy you have. So it's a volume and pressure, and volume and pressure will be completely dictated by how capable a surface is of creating volume, space, and the pressure is just how many little charge elements you crowd in there. So when you're crowding a lot of stuff in a small space, your voltage goes up, and when you have the same things but in a little more space, the pressure goes down, so the voltage goes down. So if you make more space and you don't add more pressure, pressure will go down. And as you reduce space by having, in a sense, voltage will make space, as I just pointed out, because voltage will compel things to pull more vigorously. More pressure means more attraction or repulsion over a distance. So I think that's enough of a statement for just to clarify a few things. And yeah, so that should, it's hard to draw a picture of their theory because they don't use it very consistently. But I have this idea that you can just polarize atoms, that is, turn them into dipoles. But these aren't dipoles. These atoms are monopoles. They're to the world's perspective, they're charged from all sides. So when one goes positive and the other one goes negative, they're going positive and negative as an effect to the world from any side. They're not polarized, and you only create a dipole when you have the two of them in proximity to each other, that is, attached to each other, attracted to each other, and they stick. And that certainly happens also in atoms. So you can have materials where the monopoles stick to each other, and then you can have materials where they're on opposite sides, or there's something else like that. So that's another implication of their theory, is that stuff like glass, so that's sort of relevant to the video they'll be playing, that stuff like glass, if it charges positive on one side, it charges negative on the other side. But you can sort of know that can't be right just from the experiments done, because he'll never put charge on a piece of glass and then just say, well, if I want negative charge, I just flip the glass over. Right, so he rubs cat fur on a piece of glass. He always takes the charge off the top when theoretically he could have his choice and just flip the glass over and take the charge from the bottom, and it would be the opposite charge. So why wouldn't he rub the glass vertically, and then he could choose what charge he wanted? So it doesn't just, glass doesn't automatically charge on the other side the opposite of the thing on the one side, but it certainly does if you put it between two conductors. If you charge it on both sides, you'll get it charge on both sides. That's opposite. Now that might look like something just shifted, but that's not what really happened. You put charge on one side and then you put charge on the other side. It didn't migrate through the material. Just to clarify the distinctions between what they say and what I say. I hope that helped a little bit. Maybe. Alright, so we'll play the video and then we'll have to make sure in here that it's working, because we have had some trouble.
How can I build a very large capacitor, one that has a very large capacitance? Well, capacitance, C, is the area times epsilon 0 divided by D times kappa. If your book calls K. So make K large, make A large, and make D as small as you possibly can. Yeah, but you have a limit for D. If you make D too small, you may get sparks between the conductors, because you may exceed the electric field, the breakdown electric field. So you must always stay below that breakdown field, which in air would be 3 million volts per meter. If you want a very large...
It is an interesting subject that I was actually thinking about making a dome, and then the idea is you want to put the idea is the edges are always the problem. So the real problem is there's a curvature at the edge that makes that small radius that increases the pressure there. So you might only have 300,000 volts on this surface, but you end up with 3 million on this tip. And so it's just these little edges that are the places where everything falls apart. And then it's not so much that it's going to create a giant spark to ground, it's that you get that leakage, the blue light, the St. Elmo's fire. The right technical name is, I can't remember. Yeah, lots of things to remember.
Kappa, you would say, well, why don't you make the layer water in between? That has a kappa of 80. The problem is that water has a very low breakdown.
Right, so it has this capacity, so it has the kappa of 80, which means it can hold a lot of charge. Problem is the breakdown voltage, that is, you put any kind of voltage on it, it leaks out very fast. So it's leaky. So it holds a lot of charge, but it can't hold it in a circumstance where the charge isn't well isolated from ground, or the opposite charge. As soon as you bring another charge close to it, it can leak way too easy.
electric field, so you don't want water. If you take polyethylene,
the ions move, essentially, is a way of saying it. The ions are way too free to move somewhere, and so the attractive force will wipe out your charge. I mean, the ions will combine into dipoles.
I just called it poly here, just as abbreviation. Polyethylene has a breakdown electric field of 18 million volts per meter, and it has a kappa, I believe.
So they could have just said that it's 3 into 18, which is whatever, 8, 8, 6, 7, 6.5. All right. Well, anyway, yeah, 6. Obviously, it's 6. You retard. So anyway, so it's you know, it's 6 times more than the atmosphere. So just to make that 18, when somebody says 18 million, you got to put that in the perspective of the 3 million for atmosphere. So it's not that dramatically different. It's a nice difference, but it's not that dramatic a difference.
Of 3. Many capacitors I made, whereby the layer in between is polyethylene. Although mica.
So you see the kappa number is kind of low compared to glass, so it obviously can't do that expanding the layer thing, so you can't get as much density on it. But it's very good that it won't. You can get it pretty close to the surfaces without it allowing discharges, electrical discharges.
Really superior. Be it as it may, I want to evaluate now with you 2 capacitors which each have the same capacitance of 100 microfarad. But one of them, the manufacturer says that you could put a maximum potential difference of 4,000 volts over it. That's this baby. And the other, I go to Radio Shack, and it says you cannot exceed the potential difference not more than 40 volts. Well, if I have polyethylene in between the layers of the conductors, then I can calculate.
Not too exciting to calculate it, but so the point is the 2 capacitors, even though there's a huge difference in size, are going to store a total amount of energy that's going to be comparable. It's just that, yes, one's allowing you to hold 4,000 volts, which has a huge, breakdown-wise is much higher, 100 times the 40 volts. So the pressure, one can handle a lot more pressure, and that's why it has to be so much bigger. So you can really see a difference of from 40 to 4,000 is a big difference in pressure, and it equals a gigantic difference in size, so, a million times or whatever, 10,000 times difference in size necessary. So the voltage it's proportional to size, but the proportional is, the 2 lines diverge proportionally, but one is getting as a practical matter, very big, very fast.
What the thickness D should be before I get breakdown. That's very easy, because V equals ED, and so I put in here 18 million volts per meter, and I go to 4,000 volts, and then I see what I am with D. And it turns out that the minimum value for D, you cannot go any thinner, is then 220 microns, and so for this one, it is only 2.2 microns. You can make it much thinner, because the potential difference is 100 times lower. So you can make the layer 100 times thinner before you get electric breakdown. I want the 2 capacitors to have the same capacitance. That means, since they have the same kappa, and they have the same epsilon 0, it means that A over B has to be the same for both capacitors. So A divided by D for this one must be the same as A divided by D for that one. But if D here is 100 times larger than this one, then this A must also be 100 times larger, because A over D is constant. So if A here is 100, then A is here 1.
So you need, for the small capacitor, you obviously only need, it's a 1 to 100 ratio to get both volume, but you're just basically saying it has to be volume at the ability to store the voltage. So yes, so you need less volume of material at the lower voltage. Well, it's kind of obvious.
Now think about it. What determines the volume of a capacitor? That's really the area of the plates times the thickness. And if I ignore for now the thickness of the conducting plates, then the volume of a capacitor clearly is the product between the area and the thickness.
So yeah, the volume, the thickness of the material only comes into account when that's how much current you can produce, get through the material. So if you make it super, super thin, then it can't carry very much material without melting. I mean, very much energy.
And so it tells me then that this capacitor, which has 100 times larger area, is 100 times thicker, will have a 10,000 times larger volume than this capacitor. And this baby is 4,000 volts, 100 microfarads. It has a length of about 30 centimeters, 10 centimeters like this, 20 centimeters high. That is about 10,000 cubic centimeters. 10,000 cubic centimeters.
All right, so what I said before, they're obviously not carrying the same amount of energy. So he's using the volume number, which again is the extra volume you're creating, your capacity to create the extra volume on the surface. And so this one can create a lot more volume on the surface because the voltage is higher, which means the amount of pressure you're using is higher. So the higher the pressure you're using, obviously the more you're stretching the material. So although they have on as face value the same numbers, the fact that you're using higher voltage is going to mean you're taking greater advantage of the ability of the dielectric to expand.
You go to Radio Shack and you buy yourself a 40 volt capacitor, 100 microfarad, which will be 10,000 times smaller in volume. That will be only 1 cubic centimeter. And if I had one of them behind my ear, you wouldn't even notice that, would you? Would you tell me what it says here? 100 microfarad, how many volts? 40 volts. That's small. Compared to this one, which can handle 4,000 volts, but the capacitance is the same. So you see now the connection with area and with thickness, by no means trivial.
Right, and you also kind of see that when they say capacitance, you know, I don't know whether that's the best word to use to describe what something can do, because obviously the bigger capacitor can, you know, can create a lot more wattage than so they have the same value on their surface, but their function's quite different.
All this has been very rough on you. I realize that. It takes time to digest it, and you have to go over your notes. And therefore, for the remaining time, we have quite some time left, I will try to entertain you with something which is a...
So I think, you know, the physics has the same problem. They have a lot of these connected facts, phenomenon to add up, and they've drawn certain conclusions about how something happens. And once they draw that conclusion, they just force that model to fit, instead of recognizing that in some places it doesn't fit, like the insulator argument, where you're just shifting, you know, the polarity of the material. It seems kind of clear that the insulator, by definition, doesn't do any collective shifting. That you could kind of define the insulator as a bunch of hermits, a bunch of things that really don't want to contact with the rest of the world. They don't want to be part of an internet. They don't want to be, you know, they don't want to be connected. And that defines the properties of the insulator, is that it doesn't have, the atoms don't have good communication skills.
A little bit easier, a little nicer to digest. Professor Mussenbroek in the Netherlands invented, yeah, you can say he invented the capacitor. It was an accidental discovery. He called him a Leyden jar because he worked in Leiden. And a Leyden jar is the following. This is a glass bottle. So all this is glass. That's an insulator. And he has outside the insulator, he has two conducting plates. So that's a beaker outside. And there's a beaker inside conducting. That's a capacitor.
All right, so the orange lines are copper. So he has a copper plate on the outside and a copper plate on the inside. And all that's really changed is the shape. You know, this change the shape, and you got the same thing as a copper plate, piece of glass, copper plate.
But he didn't call it a capacitor. And so he charged these up, and so you can have plus charge here and minus Q on the inside. And he did experiments with that. The energy stored in a capacitor, we discussed that last time, equals 1/2 times the free charge times the potential difference. If you prefer 1/2 CV squared, that's the same thing. I have no problem with that, because this C is Q free divided by V, so it's the same thing. What I'm going to do, I'm going to put a certain potential difference over a Leyden jar. I will show you the Leyden jar that we have. You see there. And once I have put on some potential difference, put on some charge on the outer surface and on the inner surface, you can see the outer surface there. The inner one is harder to see, but I'll show that later to you. So here you see the glass, and here you see the outer conductor. And there's an inner one too, which you can't see very well. Once I have done that, I will disassemble it. So I first charge it up, so there is energy in there, this much energy. And then I will take the glass out. I will put the outside.
So the part that's interesting, I mean, obviously this wouldn't be a story unless there's a story, right? And so the story is going to be is that the glass is holding the charge in this case. So if I made it all flat, the argument, I don't know, I've never done it. I don't know if he's done it. To see if you can charge the glass if you're using glass between two plates and you remove the plates rather than pull the glass out. Maybe if you remove the plates, I mean widen the plates, the glass will retain its charge. But that's essentially what's going to happen here, is the insulator is going to hold a significant amount of charge. But that's sort of what I argued before, is when he slid the glass in between the two plates and the system pulled voltage, is because it's got to charge the glass surface. You know, then you pull the glass back out and the voltage goes back out, was because you're stripping the voltage off based on how you pulled the glass out. But if you pulled the glass out without the conductors close to each other, the argument might be that if the conductors are further apart when you pull the glass out from the surface, that the glass will retain its charge, potentially.
Conductor here, the inside conductor here. I will discharge them completely. I will hold them in my hands. I will touch them with my face. I will.
So he goes through all this stuff when he knows it's a conductor and that it's copper, a really good conductor. All he's got to do is touch it, and he's pulled the charge off. So see, there's the other circumstances. If there's charge on glass, it's hard to get it off. You have to maybe rub it. You have to kind of do something to get the charge to come off, because it's hard to make contact with it, direct contact. And that would be my argument. That's because it's doing this fudgy surface crap. It doesn't have the surface is ambiguous. And so that would be insulators have ambiguous surfaces, and so it's hard to get the charge out of them, where the conductor has an unambiguous both surface and substrate, and will pull the charge very easily. But anyway, I just you know, these are little things that, frankly, you know, when I first saw this video, you know, 5 years ago or whatever, I might be confused by that. But so, oh, it's hard to get the charge off the copper. No, it's really easy to get the charge off the copper.
Click them. I will do anything to get all the charge off, and then I will reassemble them. Well, if I get all the charge off, all this Q free goes away. There's no longer any potential difference. When I reassemble that baby, then clearly there couldn't be any energy left. And the best way to demonstrate that then to you is to take these prongs, which are
any voltage difference is the substitute for the word energy. Obviously, you see, he touches both of them. They're both now at the ground pressure, and there's no difference, and therefore no voltage.
I have here conducting prongs, and see whether I can still draw a spark by connecting the inner part with the outer part. And you would not expect to see anything. So it is something that is not going to be too exciting. But let's do it anyhow. So here is this Leyden jar, and I'm turning the Wimhurst to charge it up. I'm going to remove this connection, take this out.
Alright, now the key point is he doesn't remove this by touching it. So he didn't put it to ground. And it's probably some political crap, but I'll have to check. Sorry. Yes, we had time to contemplate things. So he pulled the little jar out without touching that metal thing or the conductor. So that's probably a key to this thing, because if you pull the charge off the conductor while it's in the glass, it'll probably pull the charge off the glass. So there is, you know, this is a little bit, what's a little bit irritating about how they do experiments, because they've done them and they kind of know what things they're allowed to do, what they can do and what they can't do to screw it up. And some of that information is really valuable in understanding what's happening. So again, he's going to do the same thing when he tries to get the copper off of, he'll touch the glass because he knows it's not a conductor. He's not going to pull the charge off the glass, you know, because it's not a conductor. So, you know, he can hold it and it can still have charge on places. But he's not going to touch either one of those copper things till he makes sure they're off the glass.
Take this out. Come on. Believe me, no charge on it anymore. This one.
So again, he's kind of just making this physics thing. He's just sending dual messages. Look, I have to go through all this work to get the charge off a conductor. No, the conductors are easy. The glass is the thing hard to get the charge off of.
All done. Believe me.
So again, not touching it.
There we go.
Using the insulated prong, so he wouldn't touch that piece of copper and drop it in, because he knows that'll pull the charge right off the glass.
See what happens when I short out the outer.
So the point is the two surfaces are obviously really close to each other, but they're not conductive. Okay, so if you want to get the charge off the surface, you have to pull it off. You have to ask it to come off. And that's why when he uses the flat disc on the glass, he has to touch it. He has to pull the charge. And he has to pull the charge back into the conductor, because he's still going to get the opposite charge, which you always have to keep track of. He's not pulling the positive charge off the glass. He's just pulling the opposite charge that's on the conductor. He's pulling that up, which doesn't make, which is hard to figure out how the positive charge gets off the glass and turns into a negative charge. So I don't have the explanation for that one yet. I have to think about that.
Conductor was the inner conductor. Watch it.
So it's a little spark sound.
That is amazing. There shouldn't be any energy on that capacitor. Nothing. And I saw a huge spark, not even a small one. When I saw this first, and I'm not joking, I was totally baffled. And I was thinking about it. I couldn't sleep all night. I couldn't think of any reasonable explanation.
Right, so there wasn't anything in the physics he had previously learned that gave him any reason to think that should happen. And that's part of the problem, is that the physics is kind of doesn't provide you with any tools to do any dissection like that, because there's no consistent mechanism for what's happening.
And so my charter for you is to also have a few sleepless nights and to try to come up why this is happening. How is it possible that I first bring charge on these two plates, disassemble them, totally take all the charge off, and nevertheless when I assemble them again, there's a huge potential difference between the two plates, otherwise you wouldn't have seen the spark. So give that some thought, and later in the course I will make an attempt to explain this. At least that's the explanation that I came up with. It may not be the best one, but that's the only one I could come up with.
So that's a pretty telling statement. Look, physics really doesn't have a mechanism that makes this obvious. You're going to have to do some thinking on your own. And so he does his own thinking, and he'll have his explanation, but he's basically conceding, yeah, maybe somebody else got a better one. So it's sort of evidence of an incomplete theory of electricity that, you know, when you're just conceding you can't explain a relatively simple mechanical experiment. I mean, not too many moving parts here.
In the remaining 8 minutes, I want to tell you the last secret, which I owe you, of the Van de Graaff. And that has to do with the potential that we can achieve. Remember the large Van de Graaff? We could get it up to about 300,000 volts. How do we charge a conducting sphere? Well, let's start off with this hollow sphere, which is what the Van de Graaff is. And suppose I have here a voltage supply with a few kilovolts. I can buy that. And I have a sphere, and I touch with this sphere, with an insulating rod, I touch the output of the few kilovolt supply, and I bring this, so there's positive charge on here, say, and I bring it close to the Van de Graaff.
So I don't think you need this sphere thing. You just need another conductor that have charge on, and then you touch the two together to place the charge on it. So he's just saying the small thing puts charge on the big thing.
There will be an electric field between this charged object and the Van de Graaff, and the closer I get, the stronger that electric field will be. And when I touch the outer...
So again, concentrating on fields rather than concentrating on... The fact is one's going to have a voltage and the other one's going to have a voltage. And as you keep putting charge on the big thing, its voltage is going to end up equaling the voltage of the small thing, and you won't be able to put any more charge on because there won't be any voltage difference. You really don't need a field for that.
Shell, then the charge will flow in the Van de Graaff. I go back to my power supply, I touch again a few thousand volts, and I keep spooning charge on the Van de Graaff.
Yeah, it's sort of this argument. If the atoms are exchanging pressure in a sense, right? So you have a high pressure atom, an atom that is, the electrons are closer together, an electron where they're further apart, and when they hit, they share that information, and the low pressure atom is raised and the high pressure atom is lowered, and that's sort of the theory here, is that that's how you convey the charge through the atoms, and with the help of electrons bouncing between them. I'm not saying there's not any free electrons helping the process, but the process is really the pressure inside of atoms. The electrons are a reflection. The free electrons, if there are such a thing, they're not really free. They're just they're stuck near this atom loosely, and they can be thrown over here loosely, and they can loosely, but they don't really just float around. They're either kind of stuck or they're being shot off, but there's no, you know, it's stuck here. This atom has less pressure. The free electron sticks here, adds to the pressure of this atom. So it's like if this one's producing more electron force because it has more electrons, it hits into this thing or gets close, then the electron's now part of this atom. Now this one has more black energy or electron force because it's going to reflect more electron force because it has more electrons. Something like that.
Will I be able to get the Van de Graaff up to 300,000 volts? No way, because there comes a time that the potential of this object, comes from my power supply, is the same electric potential as the Van de Graaff. And then you can no longer exchange charge. What it comes down to is that when you come with this conductor and you approach the Van de Graaff, there will be no longer any electric fields between the two. So there will be no longer any potential difference. So you can't transfer any more charge. So you run very quickly into a situation which will freeze. You cannot get it above a few thousand volts. So now what you do, and here comes the breakthrough by Professor Van de Graaff from MIT, who now said, I don't have to bring the charge on this way, but I can bring the charge in this way. So now you go to your power supply, a few thousand volts, and you bring it inside this sphere where there was no electric field to start with.
Yeah, it's really, it's almost surprising that Newton didn't figure this out, or somebody, just because it really is so obvious and simple, just sneak it in, and you can increase the voltage. And yeah, like I said, it gets your imagination going. It's sort of like the argument where you're getting a little bit of free energy from gravity and hydroelectric or wind or so, and it sort of makes you think, oh, this has real potential. But there's always a limiting factor, and the limiting factor is that hole. So you can't make the hole zero. It'd be nice if you could just shove a wire through to put the charge on. But then the distance between your conductor and your Van de Graaff is going to be too small, and the voltage difference, even though you're pumping, say, 1,000 volts at a time, or even 10,000 volts, the voltage difference between 10,000 volts and the surface charge on the Van de Graaff is going to be huge, and so it's going to break down the opposite way. And now you have this, and if you leave an opening, that whole edge becomes that small surface again, and you end up with all the breakdown voltage, the little current that just will drain the voltage off the surface. So it is an interesting thought experiment.
When you charge the outside, there's going to be an electric field from this object, and there's going to be an electric field from this object. There was no electric field inside. If I now bring the charged sphere there, I'm going to get E field lines like this, problem 2-1. And so now there is a potential difference between this object and the sphere. What I have done, by moving it from here to the inside, I have done positive work without having realized it, and therefore I have brought this potential higher than the sphere. Now I touch the inside of the Van de Graaff, and now the charge will run on the outer shell. And I can keep doing that. Inside, touch, inside, touch, inside, touch. And every time I come in here, there's no electric field in there. So I can do that until I'm green in the face. Well, there comes a time that I can no longer increase the potential of the Van de Graaff, and that is when the Van de Graaff goes into electric breakdown. When I reach my 300,000 volts, it's all over. I can try to bring the potential up, but it's going to lose charge to the air.
So where the sparks you hear is probably happening is where that round part, the opening, the end of the hole, it's breaking down there. So that's the part you have to try to insulate, and insulators have limitations.
And so that is ultimately the limit of the potential of the Van de Graaff. So how does the Van de Graaff work? We have a belt, which is run by a motor. Here is the Van de Graaff. And right here, through corona discharge, we put charge on the belt.
So through the same processes that's ruining the capacity of the Van de Graaff's, corona discharge was the word I was looking for before. That's the leaking. That's the stuff you don't see. No spark, but it just leaks. And so you can use the same method to, leak voltage off by. So he's basically saying it's a bunch of little wire brushes, and so the belt goes against the wire brushes, and you're creating charge.
They're very sharp points, and we get a corona discharge at a relatively low potential difference. Goes on the belt goes here, and right here there are two sharp points.
Right. So I would argue that obviously if you were, you could just run a wire to the top part, and you could make this hole smaller. But the problem is you can't make the hole smaller, so you might as well just run the belt up there. But yes, I think it could be more efficient if you didn't bother running the belt all the way up there and just run a wire up there to place charge on the surface. But you can't have a constant connection to the charge elements, or they'll leak. So I guess that's part of the reason why they're using two subtle ways of acquiring the charge and then dispersing the charge. Through corona discharge, at least you slow down the conductor. It's almost like adding a piece of resistance to prevent discharge back through the thing you're trying to charge it with. You're taking a battery of lower voltage and essentially connecting it to a higher voltage in a sense, and so you want to make sure that it doesn't know you did that. So you want to like push it on and then make sure there's no connection for it to leak back out.
Through corona discharge, take the charge off on the inside. That's the key. And then it goes to the dome, and then it charges up to the point that you begin to hear the sparks and that you have breakdown.
It's still a conductor on the inside of the surface. It's still a conductor to the high voltage on the exterior surface. So the interior surface is still a conductor to the exterior surface. So you need some kind of mechanism to place the charge that isn't a direct, I don't know what the right word would be, that would pull charge. So it is sort of interesting. That's why you just touch. But if you touch and held, I wonder whether you would be pulling off charge. So see, another thing where just you need to do a little playing with it to figure out whether that can happen. Because it is a conductor. You're still saying it's a conductor. I should be able to pull charge off the inside because it's still a conductor.
And I can demonstrate that to you. I built my own Van de Graaff, and the Van de Graaff that I built to you is this paint can.
I mean, the truth is that obviously you can't pull charge off the inside, so you can't do it, so it's okay. So I still think the wire thing will work.
I'm going to charge that paint can.
I'm going to try
by touching it repeatedly with a conductor, and the conductor has I'm going to touch the conductor with a few thousand volt power supply every time. This is the power supply. Turning it on now, and you're going to see the potential of the Van de Graaff there. That is a very crude measure for the potential on the Van de Graaff, but very crudely, when it reads a 1, I have about 10,000 volts. This is the probe that I'm using for that.
Well, it's a lot better than that other voltage measuring thing you used before. No, but whatever. So he's measuring it at a distance, which must be some sort of, he's figuring out how much it is. So the probe is near the bucket, but not, it's a few inches. So it's going to be measuring the field and then approximating what the surface must actually be for there to be voltage at that distance. Something like that.
With 20,000 volts. My power supply is only a few thousand volts. So that's not very good. Well, I will first start charging it on the outside to demonstrate to you that I very...
See, it's very hard to measure high voltages because to measure them, you're going to create all kinds of opportunity in your wires and your circuits for breakdown voltage. So you're just basically going to create a path to ground. So measuring high voltage gets a little complicated. You kind of have to do it based on some separate system, that isn't directly connected to the voltage. So you almost have to measure high voltage indirectly, not directly.
Quickly run into the wall that I just described. That if they have the same potential, then I can no longer transfer a charge. But then I'm going to change my tactics and then I go inside. And then you will see that it will go up further. So let's first see what happens if I now bring charge on the outside. There it goes. About 1,000 volts, about 2,000 volts. 2,000 volts, keep an eye on it. 2,000 volts, it's heading for 3,000 volts. 3,000 volts, 3,000 volts, 3,000 volts, 3,000 volts. Not getting anywhere. I'm beginning to reach the saturation, maybe 3,500 volts. 3.5, it's slowly going to 4. Let's see whether we can get it much higher than 4. I don't think we can. So this is the end of the story. before Professor Van der Graaf. But then came Professor Van der Graaf, and he said, look, man, you got to go inside. Now watch it. Now I have to concentrate on this scooping, so I would like you to tell me when we reach 5,000, you just scream. Oh man, we already passed the 5,000, we've done it. 10,000, scream when you see 10,000. Scream when you see 15,000.
So a little too much theater for me, but you know, I'm just not a theater kind of person.
Scream when you see 15,000. Very good. Keep an eye on it. Tell me when you see 20,000. I don't hear anything. Now I want you to tell me every 1,000, because I think we're going to run into the wall very quickly. 21? I want to hear 22. Already at 23. So I expect that very quickly now, the can will go into discharge. You won't see that, but you get corona discharge. And then no matter how hard I work, I will not be able to bring the potential up. But let's keep going. Are we already at 2,500? 25,000, sorry, 25,000? 25,000 volts. 25.6, 27, 27, 28.
So I guess a little buzzer goes off when he's over time. I would imagine that's what that is.
28. Looks like we are beginning to get into the corona discharge. 28, boy, 28. That's a record. 28, keep an eye on it. 29. 29. You realize I'm doing all this work? Well, I got paid for it. I think I've reached the limit. I've reached my own limit, and I've reached the limit of the charging. Now we have 30,000 volts, and we started off with only a few thousand volts. Originally, it wasn't a very dangerous object, but now 30,000 volts. Shall I?
Alright, so we missed it, but apparently he touched it. So 30,000, and then there's a sorry that you did not see me touch the can at 300,000 volts. So it's kind of funny, right, that they put a message on the video and got the number wrong. I mean, 300,000 volts. No, 30,000. Anyway, take my word for it that I got a large electric shock. Okay. So anyway, just kind of funny.
Okay, see you next week.
Poor editing there. So anyway, I think we're done our job, mostly. Hopefully no glitches. And yes, so we'll move on and proceed in that way direction. So till next time, such, so forth and whatnot.